Hello friends, I hope you are all well. There is this video that you have seen in the starting of the video that is now been playing. This is a part of the video that I have seen recently in YouTube from an explanation that was given by Steve Mould about the Morse effect. And about this part of the video, there is something that isn't liked by me. Like there is something problem in this video. The thing that is there is a problem. I will discuss it in the next part. But the thing is that I want to give an explanation to this video, and this video is actually wrong. I want to give a mathematical description. After that, a very easy explanation, and after that, with that thing, I will end this part of the video. So there is one block lying on the table, and there is a bullet that is being hit at the center of mass of this block. The bullet get combined with the block, like it stuck in the block, and the block get to a certain height h1 for the first situation. And there is the second situation where the bullet hits the block at off the center of mass at some distance x from the center of the mass, and it attains the block attains some height h2, and it is so counterintuitive to see the result that h2 is greater than h1. Why I am saying after this moment. It has been seen in the second case, on the second right side of the video, that h2 is greater than h1. h2 height attained when it is hit off the center of mass is attaining more than the h1. That is so counterintuitive. First of all, let us think of the reason why this is happening. Okay, what is our experience? What is our brain saying us? What is our basic knowledge says us? That the height h2 should be less than h1. Why? Because the energy with which the bullet is hitting is giving up some energy along with the as it is getting stuck in the block, is having some energy E at the initial point. That E is only getting translated, like the energy is only translational energy in the first case, so it is attaining some height h1. That is there is having some center of mass velocity, and that is depends upon the initial energy of the bullet, and there is this energy E which has been only divided into, or not divided, or it is been only used in only the translation motion of this whole block up to a height h1. When the bullet is hitting at the left side of the or off the center of mass, there is the energy is being divided into two parts. One that is rotational kinetic energy, and one that is translation kinetic energy. The translation kinetic energy is the cause for the block to rise to a height h2. The rotation kinetic energy does not provide or what to say. The rotational kinetic energy is not the cause for the block to go height h2. It is the translation energy of the center of mass which is going to attain this block to a height h2. So if I say that the energy is being divided into rotational kinetic energy and it is divided into translation kinetic energy, the same constant E energy in the first case as well as in the second case, then the translation kinetic energy for the block plus bullet system in the second case is having less, so it should attain less energy, less height. But the situation is seen completely different. So what our brain says, it may be happening. There is no normal reaction that is being given by the ground after hitting just the block rises up. But here the normal reaction and frictional force both are acting at the block for some time. So our brain says, our experience says that the normal reaction and friction must be doing some work on this block, and it will be gaining some energy, and it is rising a much greater height. No, my friend, no. The explanation is totally different, and it is so beautiful and wonderful explanation that I am going to prove right now, and at last I will say the reason what is happening. And I thought it is a very beautiful example and counterintuitive example to solve this solution. The answer is right coming next. There is this first case. there is this bullet hitting. With speed v naught. Okay, so now I am going to take I am now going to take all the values for speed, mass of the block, mass of the bullet, and all, so that to get to a solution of height h1 that has been attained in the first case and the height h2 attained in the second case. I am drawing all the forces that are been acting. In the second case, it will turn around this corner. Why it will turn? Why it is not going up? We'll think because there is friction of the block and the table. There is a frictional force F acting. There is normal reaction. This is O point. Let it be O point. That is, this is capital M G. This is small m G. Okay. Whereas small m and capital M are M M. These are the forces here. O is the point, and in the first case, what is happening? We will see. Okay, I am taking all the values of mass. First, capital M, M initial speed, and the length of the rod. Let the mass of the bullet be. I am taking the values so that we can get a number of h1 value height attained for this one, and I can get a number value for the second case. We can compare which is greater. Or otherwise, seeing only the m, small m, m, l, v naught as the parameters, it will be a confusion, or it will not be easy to see which is greater than which one. Okay, so I am taking the value of small m as 10 gram, capital M as 1000 gram, V naught as 120 meters per second, length of the rod is 30 centimeter. I have taken like this only, small m as 10 gram, 1000 gram, V naught as 120, and length as 30 centimeter, just like that only, on the basis of my as a standard values of bullet and all these things, the velocity of the bullet that comes out of the gun and all. These are some of the values that I got from the internet, and I have taken this value. And let us see the problem. Okay, in the first case, what I can do is, first of all, I want to know the velocity of the as soon as the bullet goes into the block, it is going to get attached to the block. So there will be a combined velocity of the center of mass of the block plus bullet. So by momentum conservation, m v naught is equal to m plus m just before the collision m v naught, and just after the collision m plus m v1 cm, as it is the velocity of the center of mass. So v1 cm. So v1 cm, okay, sorry, okay, here um, the bullet is hitting in the center of mass, na? In the first situation, the bullet is hitting at the center of mass. Sorry for the wrong writings. V naught small m is the mass. Okay. So v1 cm equals to m by m plus m v naught. This is the velocity of the center of mass. That is the velocity of this point. As the bullet gets stuck in the center of mass of the rod, the center of mass of the whole bullet plus block will be this center only. So v1 cm. So with this velocity, I want to see how much height it is attaining. So by energy conservation, half m plus m v1 cm square is equal to m plus m g h1. So h1 equals to v1 cm whole square divided by 2g. So what is the v1 cm square? It is m square by 2 m plus m whole square g v naught square. Now putting all the values of v naught, small m, capital M, 2 and g, taking it as 10, I am getting the value as uh, mm, into 120 square. It is 0.0705 meter, that is 7.05 centimeter. Let us calculate the height that has been attained by the block plus bullet in the second case, that is the center of mass of the combined block and bullet. This, okay, h1. Here the thing is that here what is happening, the ball is hitting off the center of mass. I am taking that it is hitting at the edge of the block, that is of the center of mass but at the end of the block. Okay, so now what will happen is the block will try to rise up, because as it is having forward momentum. So the combined center of mass, that is at the end of the combined center of mass will shift towards left, like the block center of mass was here. After combining with the bullet, it will shift towards left. It will try to rise up, but what will happen is, as it will try to rise up, this point will try to slide on the table, but the frictional force will act and it will not try to slip this point. A normal reaction as it is in contact with the table will be applied on the rod. This frictional force will not let this point of the block to move. So now this will be a pure rotation about this point for some moment. Why I am saying for the some moment? I am saying that. Wait. So what I am going to do? I am going to divide this as theta. I am write it as theta. So this will be theta and this will be theta. So what I am going to now do is, and as this will be theta, frictional force making an angle theta with the tangential direction. Why this is tangential? I am saying what I will do is I will resolve the forces in tangential and in the radial direction of the block, in the radial direction and in the tangential direction, so that it will be easy for me to solve the problem. What I have done is, I will write the force equation. First I will write the equations, that is force equation, that is along radial direction, along first radial direction. Along radial direction, the forces which are acting is whatever the forces which are acting along the radial direction will be mg cos theta plus mg cos theta minus n cos theta minus f sin theta is equal to m VCM. This will be VCM m plus m, that is now it is combined, m plus m VCM after the collision. After the collision, what is the velocity? As we got after the collision, the velocity of the center of mass we got is this one. It will be same. The velocity of the center of mass was this after the collision. Just before the collision, after the collision, we have written the momentum conservation, and we have got the velocity of the center of the mass as this. Whereas the center of mass was this at the center at the first case, and it will be off the center of the block at some this point. Let the distance of the center of mass from this point, that is pivot point, be r1. Let it be r1. What is the r1 value? I will solve there. The r1 value is how much? R1 is the r1, or better to say rcm1. Okay, better to say rcm1. So rcm1 will be what? We know it will be m l plus m l by 2 divided by m plus m, that is 2m plus m divided by 2m plus m into L. This is the distance of the center of mass from this pivot point O. So the distance of the center of the mass from the pivot point O is this 2 small m plus m divided by 2 m into L. Okay. So this is my okay. So along the radial direction, the forces are these. That is m plus m v1 cm square divided by r cm. Okay. This is my first equation. Along tangential direction, along tangential direction, the forces which are acting is mg sin theta plus mg sin theta, that is capital Mg, plus f cos theta minus n sin theta is equal to m plus m a theta, that is tangential acceleration, whereas v1 cm square divided by rcm is radial acceleration, ar. This is a theta. Now what are my variables here? You see, it is theta and f v1 cm. So we have and n f theta v1 and a theta. So we have 5 variables and we have 2 equations. We need one more 3 equation, but I will say that n will become 0 because we want to know why I am writing this equation. So first you should know I want to write this equation because I want to know at which angle this mv square by r will be less than this value. If mv square by r becomes less than this value, sorry, okay, so let me say why I am writing these equations. So I want to know that when m plus m v1 cm whole square divided by rcm is going to be greater than this value, as theta is varying, n and f is also varying, mg and capital Mg are not varying, but theta, n and f are varying. So this variation is going to bring in such a change that this will become less than this value. Less than this value, this will become less than this value, and as soon as this will become less than this value, so my mv square by r cm will be greater than this value. So in the radial direction, we can say this is the centrifugal force, that is m plus m v square by rcm is going, this is centrifugal force direction, is going to be greater than all the forces acting in the radial direction. So it will lose contact from the surface as soon as this happens. So this is this mv square by r is going to be greater than this value, as the n, f and theta are varying. Okay, so till the point they are in contact, they are in contact, this equation is valid. But the point this becomes that instant this becomes greater than this, this point is going to be losing contact, as the centrifugal force is going to be greater than this radial forces, all the forces acting in the radial direction. Or in the other words, we can say these forces becomes less than this value, as the nf and theta value are varying. This will make this one less than this thing. Oppositely, vice versa, we can say that. So this is going to lose contact along the radial direction. The centrifugal force will be greater than all the force acting the radial force. So this will lose contact, as we have seen on the video also. After some angle, it is losing the contact, it is going up. So we want to find the theta at which this is going to lose contact. For that I am writing all the equations. This is force equation. I can write one torque equation. Okay, so I can write torque equation. That is, what is the torque equation about this point or pivot point? That is mg L sin theta plus mg L by 2 sin theta is equal to torque is equal to net torque acting on the system is equal to m plus m, that is m plus m RCM square, that is I alpha that is angular acceleration, alpha. And we know in pure rotation alpha is equal to, since a theta is equal to alpha RCM in case of pure rotation. So RCM, so alpha will be equals to a theta by RCM. So we can write m plus m RCM a theta mgl sin theta plus mg L by 2 sin theta mgl sin mgl by 2. This is my equation 3. And one more equation what we can write is the energy equation, energy conservation after the collision of the bullet. Okay, energy conservation after the collision of the bullet, what energy it is having, that energy is going to be converted into potential energy, that is it is some attaining some height, the center of mass RCM, that is, let me put R1 value here, that is R1 cm, so that you can know R1 cm. Okay, okay. Now see, by writing energy conservation, what I can say is, by energy conservation what I am saying is, just after the bullet has hit the system, what energy the block and bullet is having, that energy is going to convert to some height, that is the center of mass is attaining some height, that is potential gravitational potential energy plus rotational kinetic energy, because it is having since pure rotation. So by energy conservation I can write half m plus m VCM, that is V1 cm, that is V1 cm whole square. After the bullet has been embedded in the block, what is the center of mass velocity? V1 cm square. It is just in this position. This is t is equal to 0. This is at situation t is equal to t. So half m plus m V1 square energy conservation is equal to, what is the value? As the RCM, that is the center of mass, is attaining some height. Okay, so my gravitational potential energy will be m plus m R1 cm cos theta, gravitational potential energy plus what was the V cm or center of mass velocity at that instant when the theta is going to lose contact. Okay, theta is going to lose contact. So I haven't put the situation that theta is going the point of contact is going to lose contact. I have not put the situation, but after this point I am going to put the situation that these all are the cases. Now this is the case in between, when it is in pure rotation, between before losing the contact and after collision with the bullet. This is the instant between these, all the four these equations are. But as soon as I put normal reaction equals to 0 here and here, these situations become, these all values becomes at the point where it loses contact as soon as I put it. Okay, So small m plus m r1 cm cos theta, there is gravitational potential energy, plus half m plus m. I want to take the velocity that it is having at that instant is equal to v2 cm whole square. Okay, so I have to also write that what the things are. So okay, we know v1 cm is the velocity of the center of mass after the bullet has been collided. v2 cm is the velocity of the center of mass when the block is going to lose contact from the table. So okay, I will say okay, v2 cm square. So this is my fourth equation. See, we have five variables. What? Normal direction theta f, v1 cm that we got. Okay, a theta. See. So what is we are having five variables. Normal direction f, n, f, theta, v1 cm, a theta. So we have five variables. How many equations we have? 1, 2, 3, 4. So what all forces and torque equation, energy conservation, all I have written. Okay. So after that we can see that we have to we have five variables, but we have four equations. So by this situation, what we can solve is so now as I have written all the equation. Okay, so now what I want to know is I want to know that theta at which the block is going to lose contact from this point. So if I want to know that theta, now I have to put the normal reaction and the value of normal reaction 0 at point O. Okay, because at that point only when the normal reaction becomes 0, it is going to lose contact. So I will now having five variables instead of five variables. I am going to having four variables, and I am having four equations. I can solve that. So after putting normal reaction equals to 0, I get two equations that I have written below as for as equation 5 and equation 6. Now using equation 3, 4, 5 and 6, I can get the value of theta at which it is going to lose the contact. I am going to get that. Okay, sorry. The value of as I want to, I am writing the radial forces. I am writing the radial forces. The forces along radial direction is equal to v1 cm m plus m v1 cm square by rcm. This is not going to be v1 cm square, but it is going to be v2 cm, because v1 cm is just the velocity of the center of mass just after the collision. But I want to know at an instant theta, so I have taken it as v2 cm. Okay, and so what is v2 cm, and this v1 cm also is going to become v2 cm square. Okay, so this is going to be v2 cm square, and this v2 cm square is actually becoming the velocity of the center of mass at the time of losing the contact, where the normal direction is becoming 0. Okay, for my situation, as I want to find the theta at which it is going to lose contact, after that I want to find this v2 cm at the time of theta. Okay, so what I need to do is, first I need to eliminate f here. By how I can eliminate f? By putting the value of f from here to equation 6 in equation 5. Then what I can do is I can eliminate v2 cm by putting the value of v2 cm from equation 4 in equation 5. Then I can eliminate a theta by putting the value of 3, and by putting the value of equation 3 and equation 6, and so on. Okay, let us do it. I'm going to put it aside. I'm going to put it aside so that I can write equation 4 and 9 from equation 4 and 9 we get what is the, we have to put the value of cos theta that will be cos theta L and v1 cm to get the value of v2 cm, that is the velocity at the time of living. So the equation is what? This is v2 cm square equals to I'm writing directly by thinking, so I have to write less step. v2 cm square equals to v1 cm square minus 2g r1 cm cos theta L. Okay, cos theta L at the time of living. So my v1 cm value I know, that is v naught, that is m square v naught square by small m plus capital M whole square minus 2g. R1 cm value I know, that I have taken out. R1 cm is how much? 2 small m plus capital M L by 2 small m plus capital M. Capital M. Cos theta L, the value of cos theta L from equation 9, that is this. How much? Value is m square v naught square by 3 small m plus capital M. Two got cancelled, G L as well as L G got cancelled, 2 small m plus m and 2 small m plus capital M got cancelled. The remaining thing are m square b naught square by 3 small m plus capital M whole square. So now the value is 2 m square b naught square by 3 small m plus capital M whole square. This is my value of v2 cm square. So the value of v2 cm is how much? Root over a 2 by 3 m b naught by small m plus capital M. This is the value of v2 cm. After finding v2 cm, what I need to find is I need to find the angular velocity of the center of mass. Okay, the angular velocity, not the angular velocity of the center of mass about the point O, and which will be corresponding to the angular velocity of the whole system about the center of mass. How that is, I am saying you. Okay, the value of v2 cm we got. Okay, now see the rod. Okay, this is the rod. We know the instantaneous axis of rotation. Just leaving the surface at theta equals to theta. This is my instantaneous axis of rotation, because at the instant when it is leaving, my instantaneous axis of rotation was point O, and my center of mass, that is COM of the whole system, was this one, which is value of R1 cm. the value of r1 cm, that is the distance of, okay, this is the value of r1 cm. Now we know by the instantaneous axis of rotation concept, the angular velocity with which the center of mass move about the instantaneous axis of rotation is the angular velocity with which the whole system is going to move about the center of mass. This is the concept when there is a rotational and translation motion going on. Since after the leaving, the rotational and translation motion is going to happen, it is going to rotate about the center of mass, and the center of mass is going to move up. The instantaneous axis of rotation concept says that the angular velocity of the center of mass about point O, that is an instantaneous axis of rotation, is equal to the angular velocity with which the whole system is going to move about its center of mass. So about instantaneous axis of rotation at theta equals to theta L. At theta equals to theta, this is the instantaneous axis of rotation. Omega about O, that is the omega of the rod plus bullet system about the O, is equal to, we know omega is equal to v2 cm, the velocity will be at the time of leaving divided by rcm, that is r1 cm. Okay, omega naught is equal to v2 cm by r1 cm is equal to, what is value is going to be becoming equals to omega cm, that is the angular velocity with which the whole system is going to rotate about its center of mass. This is my value, so I need the omega cm, because just after the leaving I need what is the omega with which the rod moves about its center of mass. The rod moves about its center of mass, so my omega cm value will be how much? v2 cm, the v2 cm value I got here at the top, root over of 2 by 3 m v naught by small m plus capital M, and the value of r1 cm I know. What is the value of r1 cm? That is I can write it as 2 small m plus capital M L 2 small m plus capital M. So my small m plus capital M is getting cancelled, and the thing that I am having at the last is root over of 2 by 3 m v naught divided by 2 small m plus capital M into L. This is the value of my omega cm, that is the angular velocity of the whole system about the center of mass just after leaving. Now what I need to find the center of mass, I need to find is moment of inertia of the whole system about its center of mass. Why I need that? Because this omega cm is the omega with which the whole system moves about its center of mass. So I need also icm, such that I can conserve the energy from this position to the maximum height. From this position to the maximum height I can conserve the energy. And see the thing, okay, so why I am doing the energy conservation? I have said that normal reaction and frictional force are not doing any work. Why that is? This seems so counterintuitive, because normal reaction and frictional force are acting on the body. So when a force is acting on the body and the rod is moving, so they should be doing some work on the body. But there is a very interesting thing about the normal reaction and friction force that I have noticed, that I am going to share with you. So normal reaction and friction force are not doing any work. Okay, so what is that thing? I will say that's why I am able to apply this energy conservation. The energy at this instant when the rod was lying, the rod plus bullet system is equal to energy at this position at theta equals to theta L, and the energy at the maximum height position. Okay, so I need to find I can, okay, energy conservation. Let us apply energy conservation. I need to find the moment of inertia also, but let us find energy conservation. So how the energy conservation applies? The energy at the bottom when the bullet and block got stuck, m plus m v1 cm square equals to energy at this position. Energy at this position is how much? Half small m plus capital M v2 cm whole square plus the gravitational potential energy of the center of mass, that is small m plus capital M G R 1 cm cos theta L equals to the energy at the maximum height. What is the energy at the maximum height? This omega cm is not going to change because this is the angular velocity about the center of mass, and just after the leaving only the gravitational potential energies are working. And gravitational potential energy, the net torque of the gravitational potential, not gravitational potential, the net torque of all the gravitational force of all the points about its center of mass is 0. So the omega cm is not going to change when it rises up, and after the rises up also, at the air the omega cm is going to be the same. So at the maximum height position at h2, there will only going to be rotational kinetic energy, no translation energy, because as it is at maximum height. So half ICM, that is the moment of inertia of the whole system about the center of mass, omega cm square plus maximum height is at it has attained, so m plus m g h2. So now I need to find ICM. So let it be my equation number, how much it will be, 10, this will be 11, and this will be equation number 12. Let us find now the value of ICM, moment of inertia of the whole system about its center of mass. ICM. Okay, so what I need to now know, this small m is attached here, the capital M is at the center, the moment the center is here, and I need to know what is the moment of inertia of this small m and capital M about its center of mass. It will be how much? ICM will be small m into the distance of small m from the center of mass, that is by using the center of mass formula we can take out, that is m L by 2 small m plus capital M, this is mr square, plus capital M into distance, square of the distance of the capital M from the center of mass, that is m small m L by 2 small m plus capital M whole square. Okay, so this is this thing of distance of the small m from the center of mass, this, and the square of this you can take out by using the coordinate the center of mass formula. That is easy, you can do it. Small m, so I am not doing it here. Small m, what is the common we can take? Small m capital M L square by 2 small m plus capital M whole square, small m plus capital M equals to m capital M L square by 2 m plus capital M. This is the value of ICM. It is going to be question number 13. So okay, here it is 2 square, so it will be 2 square here. Okay, and there will be 2 here also, because here is a 2, so it will be 2 here. Now this omega cm is not going to change. Okay, because this omega cm is not going to change, because the to change omega there should be a net torque around the center of mass, but just after the leaving the whole system, the net torque about the only force that is acting is gravitational force. The gravitational force net torque about the center of mass is 0. It is 0 about the center of mass. So the omega cm is not going to change after leaving the contact of the table. It is going to be same, just only the vcm v2 cm is going to change and become 0 at the maximum height. Now what I can do is I can equate these two equations, that is this and this, to get the value of h2. By equating these two I will get nothing. I will get nothing, just it will be equal. And by equating this and this, by putting the value of ICM that I have got here, omega cm that I have got here, and v1 cm that I have got in the first case in the initial point, I can calculate the h2. Okay, let's calculate h2. So how much equation I will get? From equation 11, 12 and 13. From equation 11, 12 and 13, what I will get from equation 11, 12, 13? We'll get the value of H2. How we will get? Let us find out. So it will be half m plus capital M. Okay, V1 Cm square equals to half ICM, that is the ICM value is this, M capital M L square by 2 square small m plus capital M. Okay, omega Cm square, omega Cm value I can get from here, that is will be 8 by 3 m square V naught square by 2 small m plus capital M whole square L square plus small m plus capital M G H2. So it will be all order, so 8, so it will be 1 by 3. Now putting the value of V1 Cm also, that we know, half small m plus capital M, V1 Cm will be m square V naught square by small m plus capital M whole square, 1 by 3 m cube capital M L square, and L square got cut, this 8 and 8 got cut, m cube capital M cube V naught square divided by m plus capital M 2 small m plus capital M whole square plus small m plus capital M G H2. So I'll get the value of H2 small m plus capital M H2 G as m square V naught square by 2 small m plus capital M minus 1 by 3 m cube capital M V naught square by small m plus capital M 2 small m plus capital M. Let us take common, m square V naught square by 2 2 m plus capital M. Okay, what I will get, 1 minus 2 by 3 m small m capital M divided by plus capital M, so 2m plus capital M. I will get the value of H2 as m square V naught square by 2 small m plus capital M whole square G, 1 minus 2 by 3 small m capital M by capital M small m plus capital M 2 small m plus capital M whole square. So this is the value of H2 that I am going to get. Now see, this H2 value is what? This H2 value is the height of the center of mass from the table, from the ground level. Why? Because see, the energy conservation says that the energy just after the bullet has hit the block, that is this energy, is going to be equal to the energy at the theta L, that is translation kinetic energy plus only translation kinetic energy. Since it is pure rotation, so it is translation kinetic energy as well as this is rotation kinetic energy. At that point both are equal, not both are not equal, but both are same. There is been no distinction between them at that theta is equal to theta L. This is translation kinetic energy as well as this is rotational kinetic energy at that point, plus gravitational potential energy at that point equals to at the maximum height. At the maximum height, that height of the height of the center of mass will be from the ground level will be h2, capital M plus small m g h2, and only there is going to be rotational kinetic energy, no translational kinetic energy. So this suggests that this h2 is actually the height of the center of mass from the ground level. So I am going to get directly the height h2. See here, actually comparing this thing with with okay, comparing this thing with here h1. So actually this is h1. See, m square v naught square, m square v naught square 2 small m plus capital M square g. This is h1. So see, h2 is h1 into this. Whether this fraction is less than 1 or greater than 1 is going to decide whether h2 is greater than 1 or smaller than 1. So this is actually h1 1 minus 2 by 3 m capital M by small m plus capital M 2m plus capital M whole square. This is going to be my h2. Seeing this thing, this fraction is less than 1 because 2 is less than 3. Small m into capital M is obviously going to be less than this thing. So this is less than 1. 1 minus something 1 minus something less than 1 is going to be less than 1. So my h2 is smaller than h1. But let us put all the values that I have taken, small m, capital M, all the thing. But it is 1 minus 2 divided by 3 into 10 to the 4 divided by 3 into 1010 into 1020 into what is the value of h1? h1 was into 0.0705 meter in meter. So I am getting h2 by putting the value. I am getting a 7.04 9 centimeters. See, the value of h2 is 7.049 and the value of h1 that I got is 7.05 centimeters. So the height that is going to be attained by in the second case is going to be less than this. Even if the difference is so small, it is very hard to notice because I think because for the situation that I have taken, like for the values that I have taken, for the value of small m, capital M, v naught and L, I have taken in such a way that the value of h2 is very it is very less difference than 7.05 centimeter. Like h2 is very not less than h1, but h2 is less than h1. I think just because due to the values of small m, capital M, I have taken, my answer is not much different than h1. The difference is very less, but there is a difference. h2 is less than h1, and I am going to show you in the video. The video has been rigged. The video has been hampered, has been tempered. Okay, the video has been tempered because there are two situations shown. One in which the first case and second case were shown after some interval, and there is this video where both the videos has been shown at the same instant. So they are totally different. I will show you them, and what is happening I will say. Okay, now what I have got is, see in the video, see the height no see in the video, in the second case, the height that has been obtained by the whole system is just touching the ruler or just nearby the ruler at the top end of the ruler, as well as the height that has been attained by the block bullet system in the first case also till the ruler. Means the height difference is very less. h2 is actually less than h1 mathematically, and just after that video the both situation has been shown simultaneously. See, the h2 is so much greater than ruler, like so it is going much higher than the ruler. So this video has been made falsely. I think the bullet speed has been greater in the second case when shown in the second part of the video, and due to which it is attaining more height. Okay, so the video has been rigged or tampered just to show that H2 is greater than H1 and normal reaction and friction force are doing some work, and that is how they are attaining greater height in the second situation. Okay, but the video has been see the previous case also, like the first part of the video. When the bullet was hitting off the center of mass, it is attaining the height till ruler, as well as the block in the first case also attaining the height till ruler. Means the difference between the both the height is very less, but H2 is less than H1. That we have calculated mathematically. See, H2 is less than H1. We have calculated mathematically. And I have calculated this H2 by saying that the normal reaction friction are not doing work. Why they are not doing work? I am saying wait for that moment. Okay, and in the second part of the video, both has been shown simultaneously. See, H2 is so much greater than H1. Okay, so the video has been rigged. The video is tampered. Okay, so H2 is actually less than H1. Okay, now come the point. Now come to the point. The main part, the main thing that explains everything here. All are saying that normal reaction and friction are doing work. I am saying it. Okay. First, let us understand what is normal reaction and frictional force does to a body. Okay, or any force, any contact force does to a body. There is this block. Okay, when I am putting some contact force on this point, only this point get affected by this force, and this point being being held by the electromagnetic force by all those points in the block. If this point moves, this is going to attract this as they are held together by strong electromagnetic forces and means electromagnetic interactions, and these points are attached to these points. These points are attached to these points. In this whole way, the force that I am applying is transferring into the block. That is, this point of application where the force I am applying F is going to move under my action of force. Just that this point is interacting and held by all the atoms nearby is going to be held by these atoms. This point when it starts moving, all the points along with this starts moving under the application of force. Then I can say that my force is able to do work, move, and there is F is able to do work if all the points move together. That is, all the points as whole move together for rigid body. It is for rigid body. Okay, rigid body. Okay, so this is how contact forces work. And see here the rod which is rotating about the center of mass. Okay, about the not center of mass, it is rotating about point O. Okay, see the normal reaction and the frictional force. These are contact force. This normal reaction is only applied at the point O of the rod, not at all the points of the body, just like gravitational force. Gravitational force is a non-contact force, so it is acting on all points of the body. But the normal reaction and friction force are contact forces. They are only acting at this end of the rod. And since this end is not moving till theta L, at theta L normal reaction becomes 0 because this mv square by r centrifugal force is greater than all the force acting radially. So normal reaction is going to be becoming 0. Till that point, this point is not moving. This is still. So normal reaction and frictional force is not able to move this point. So the normal reaction and frictional force are not able to transmit this message towards all the points of this bullet system. So normal reaction and frictional force are hence doing no work. Hence my mathematics of taking energy conservation is correct. That is, gravitational potential energy and translation and kinetic energy is being conserved after the bullet has been hit with the block. After the, because before that, before hitting the block, no, before the collision and after the collision, it has been inelastic collision because the bullet has been embedded in the body. So in inelastic collision, energy is not conserved. Okay, so just after the bullet hits the block, after that the energy is going to be conserved. Just because the normal resonant friction force is not doing any work in moving this point, hence the message is not been traveled to throughout the rod of the force that has been applied with the normal resonant friction force. Hence the center of the mass of the body or the whole system is not moving due to the force applied of the normal resonant friction force. Hence my energy is conserved. Hence H2 is less than H1. And as you can also see in the video, in the first part of the video where they are showing the first case differently and the second case differently, see the height that the block is at. Both are just touching the ruler, and the difference is very less. Just like same here, H2 is less than H1. Okay, so I hope this is very interesting problem, since we have known some new thing about the normal resonant friction force working, and the normal resonant friction force are contact forces, and hence contact forces work differently than the non-contact forces. That is the thing that we have known here. Okay, so